Uh, those of you online, can you confirm again if you are hearing me clearly now? Can somebody confirm if you're hearing me
Yeah.
clearly? Okay, thank you so much. Okay, so once again, I want to welcome you to my lecture today, and this is going to be the last topic in the semester. Of course, next week we're basically going to start revision, where I'm going to walk you through, some, exam practice questions. So, but I want to say this, what we want to do today is not going to be part of the final. This is not in the textbook. I told you what we did on Wednesday. It's not also in the textbook, and it's not going to be part of the final. But why am I, giving you this information is because of the fact that you need to know, you need to have this information. Okay, you need to have this information. You know, and that is the reason why I believe I need to give it out. Okay, before I go into this now, I quickly want to have a recap. The idea behind this course, the reason why you are taking this course is because we basically want to expose you to, a way to figure out an appropriate statistical model you can use when you want to characterize relationship between variables. And you know what? Uh, before you can actually take a correct decision, before you can actually rely on the result that you get using a particular statistical model, that the reliability of that result depends on whether you have used an appropriate statistical methodology. And that is the reason why it is our job to ensure that at at a particular point in time, you're basically going to use the right statistical methodology, because we don't want a situation where you're going to mislead. And that is why we're trying to guide you. And you know what? If I want to build a statistical model to characterize relationship between variables, we got a lot of assumptions. And you know what? In addition to the assumptions, we have, the response, the nature of the response variable is very, very important. The nature of the response variable will basically tell us what statistical model are we going to use in characterizing the relationship between variables? Let me just say this. When I'm trying to look at the relationship between variables, and if the response variable is continuous, of course, I'm going to use linear regression. I'm going to say that again. When the response variable is continuous, and I want to characterize relationship between variables, in addition to other assumptions underlying linear regression model, we're basically going to use linear regression. But what if in a situation where the response, and when the response variable is continuous, the predictor could be continuous, could be categorical, could be the mixture of the two. We can still use linear regression, provided other assumptions hold, like linearity, normality, constant variance, absence of an outlier, and so on like that. Now, situation where I still have the response variable is still continuous, but the predictor variable is categorical. Then I can use analysis of variance. In that kind of situation, it means I'm basically comparing response at different levels of the categorical variable. And we can also have situation where, in addition to the categorical predictor, we can also have a continuous predictor. In that kind of situation, I can still fit a linear regression, and I can also do analysis of covariance. Okay, Of course, I demonstrated to you in this class relationship between the analysis of variance and the regression analysis. Now, I also walk you through a situation where if the response variable is now categorical, what are we going to do? Then the fact remains that the conventional linear regression model is not appropriate anymore. Then what we're basically going to use in that situation is logistic regression model. And you know what? When I was walking you through logistic regression model, when I also wanted to know we have the variance of logistic regression model. When the nature of the response, if it has two levels, we're going to fit binary logistic. When it has more than two levels and they are ordered, we're going to fit ordinal logistic regression. When we have more than two levels and they are not ordered, we're going to use multinomial logistic regression. You can say we have different, even within the logistic regression, we got the variance of logistic regression. Okay, you know, if you take a look at that, and I also walk you through a situation whereby the two variables are categorical. The response variable is categorical. The predictor variable is also categorical. We can use a chi-square test that we now call that kind of situation analysis of categorical variable. And I also walk you through, you can also use logistic regression too. But you know what do I have for you today? What I have for you today is when the nature of the response is not continuous, is not categorical, but a count. There's a difference between when data set is continuous. When the data set is continuous, it means you have values in the interval, right? When it is categorical, basically going to have label, right? 0, 1, depending on the numbers of levels. But right now, we are not talking about categorical response. We're not talking about continuous response, but we are talking about counts, discrete. Another name for that, discrete, where you can express the data set in terms of whole numbers alone, whole numbers. You can only have whole numbers. That's how we say count. Okay, if the response variable is a count, and you are looking at the relationship between response variable, that is a count, on some predictor, you can no longer fit linear regression. You can no longer fit logistic regression. You cannot fit any form of logistic regression, but the appropriate regression is Poisson regression model when it is a count. Now, I'm going to give you an example now. I have a lot of example here. The number of persons killed by mule or horse kick in the Prussian army per year, that's a count data. Okay, you can't tell me 7.5 people killed. You can't tell me 10.4. It has to be a whole number. Take a look at that. Okay, another example here is the number of people in line in front of you at a grocery store. When you go to a grocery store and you just queue up, you got a lot of people in front of you. What do you think could determine that? Probably, maybe that is, oh, maybe that's an holiday period. Or maybe the store offered discounts. I could remember what happened on Black Friday, where, the restaurant, they offer a lot of discount, and that will attract a lot of customers. So the number of customers in front of you, this is count data. You could have 0 customer in front of you. You could have 1, you could have 2, and so on like that. Okay, if you want to look at the relationship between this and what could cause that, you're basically going to fit Poisson regression model. Another example now, the number of award, okay, earned by student at one high school. Okay, the number of awards, look at that number of awards. You could win 0 or 1 or 2 or 3. That's a count. Then what determines that? What determines that? It could be the type of program the student enroll into. Could be vocational, academic, or general. And not only that, what about the final exam, like the score that you have? Because before you can actually win an award, of course, they're basically going to look at your performance. Take a look at that. If I want to fit any of this, I'm basically going to use a Poisson regression model. Okay, now in the last election, presidential election conducted in the United States, there was a certain political party alleged of irregularity. Okay, but you know what? If you now want, if you look at the electoral, if you look at United States in terms of conducting election in the Committee of Nations, United States has integrity. And somebody is going to say, yeah, are you sure can that happen in the US? Which is basically a rare event. But the fact that it's a rare event does not mean it can happen. We use Poisson distribution to model real events that occur in the blue moon. For instance, if I want to know in a particular county how many cases of a fraudulent act in the election they record, a particular county may be 0, another county may be 5, and so on like that. That's a count data. Okay, now I wanted to see the picture between the linear regression, logistic regression, and the Poisson regression. Poisson regression is also called log linear model. I wanted to take a look at the table now. Okay, because in the Poisson regression, you know what we did? We also did, in the logistic regression, we did a logic transformation of the response, right? But what do we do? What do we do in a Poisson regression? We did not did logic, but we did a log transformation instead of a logic transformation. And that is the reason when you take a look at the regression type now, you're going to see linear, logistic, log linear. Now the outcome variable for each other, when I talk about linear, that is normal. And that is the reason why we said one of the assumptions in the linear regression is normality. But when you take a look at that of logistic is binary, and that of the log linear is Poisson, the one we're dealing with now. Okay, and what I'm trying to tell you now, when you take a look at the link function here, okay, when you're talking about linear regression, we're talking about the mean, the expected value, expected value of y given x, which is equal to beta naught plus beta 1x. This is mu. So that is the reason why I call the function, the leaf function is f of mu equal to mu. But in the case of logistic regression, it is a log of odd. You know that, right? The log of odd, which we call the logic transformation. But as for the Poisson regression, it is basically going to be the log. And that is the reason why we call Poisson regression. Another name for that is log linear model. Okay, now what I want you to see now, how do we write Poisson regression model? The difference between, if you take a look at what I have now, the Poisson regression model is the log of expected value of yij equal to the log lambda ij equal to the log lambda plus the log alpha I plus the log yj. So what is the meaning of each of them? The lambda ij is actually the predicted rate. What kind of rate are we talking about? Could be the rate of disease. It could be an incidence rate. It could be the rate of a fraudulent practice. It could be, and so on like that. Take a look at that. And we're basically going to have the lambda ij is just going to be the predicted rate for the ith row and jth column of a contingency table. And we're going to have lambda, which is just the baseline rate. Okay, I just wanted to take a look at that. And you know what? I think I'm going to, for you to really understand, I'll basically take you to an example. Okay, now take a look at this example. We basically want to predict. We want to explain, we want to test the significance of some predictor on the number of customers visiting store from region. The response variable is not categorical here. The response variable here is not continuous. The response variable is a count. Because take a look at why number of customers visiting store from region. We basically want to look at the effects of 5 predators. Number one, number of housing units in the region, the average household income, the average housing unit age in the region, distance to nearest competitor, and the average distance to Sterling mines. I could remember if let's say I want to buy something now, I can say Wendy near me. Near me, I'm talking about that. It means I'm considering distance, right? But that is why you also want to look at the average distance to the store. Does it have effect on the number, of the number of customers the store will attract? That's basically what we want to tell. Here, you can use linear regression. You cannot use logistic regression, but you're going to use Poisson regression. But let me tell you now, what are you going to say that will determine the type of regression that you're going to fit? You know what? It is the nature of the response variable. The outcome variable, whether it is continuous, whether it is categorical, whether it is a count, is actually going to be a determining factor on the type of regression that you're going to use. For this one now, we basically want to use Poisson regression because of what? Because of the fact that the response variable is a count. And let me tell you this. When you decided to use, when you ignore that, when you use linear regression, you're going to have a result, but you cannot trust your results. Because there's going to be violations of assumptions. Normality assumption will be violated. Other assumption will be violated. Okay, if you don't know, if you basically want to try linear regression on that, you're basically going to see at the end of the day, by the time you are revisiting assumptions will be violated. Okay, now in this particular data set now, we actually want to consider 110 regions. Okay, we have 110 regions. That's why n equal to 110, which is the sample size. Okay, which is the number of observations. Okay, now if I want to do this, what is the model? What if somebody asks you to write, what would be the fitted Poisson regression model? Oh my God, that's so easy to write. It is just, look at that, log of lambda I equal to beta naught plus beta 1s1 and so on like that. What is the difference between this and the multiple linear regression? The difference between this and the multiple linear regression is where you have a log lambda I, you normally have y, right? That's why that is the difference. Take a look at that. That is a difference. Okay? That is a difference. Y equal beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 and so on like that. This is for the linear regression. Look at that. The difference is just y. For the Poisson regression, is basically lambda I. Okay, you're gonna write log lambda I. And let me tell you this. Every statistical model has a probabilistic component. The probabilistic component is what we call the random component. In the case of a linear regression model, the probabilistic component, the error follow normal distribution. But in the case of a Poisson regression model, the y follow Poisson. Look at that. The y, the response variable, does not follow normal distribution now. It follows Poisson distribution. Now I'm showing you now, this is this part of the data set, like I said, we want to use 110 regions. And in each region, now let me tell you what it means. This is region number 1. In region number 1, they have 9 customers. And in that particular region, they have 606 housing. And the income, the average income in that particular region is 41,393. And the age, the average, the comparator, the store. Take a look at that. We have that for over 110 stores. And what are we actually looking for? We basically want to look at the effect of some predator on, customers arriving store. Customers, let me tell you this. Customers going to store, they go to store randomly. That's purely random. Okay. And that is the reason why it follows a Poisson distribution. We use a Poisson distribution to model a real event. Real event. Okay. We use Poisson distribution to model a real event. And you know what? When you try to look at the probability distribution of the customers, which is the response variable here, is basically going to be skewed to the right. It's going to be skewed to the right. You're going to have a positive skewness. Okay, now take a look at this now. This is the data set. Now, you know what I'm trying to do now? For us to be able to justify a linear regression is not suitable. The linear regression is not appropriate. We try to look at the histogram of response. Before you can use a linear regression, of course, the histogram of the response have to be normal. You know that, right? But right now, it is skewed. Look at that. That is skewed. And you know what? Poisson regression is skewed. Poisson distribution is skewed. Therefore, if the Poisson distribution is skewed to the right and the data set that is in display is skewed to the right, then it's basically going to use Poisson regression model. Now, I'm going to show you the code now. Take a look at the code now. What is the difference between the code for Poisson regression and for linear regression and for logistic regression? If you want to write for Poisson regression, you're going to write GLM. Look at that, GLM. Don't forget, when you want to fit conventional logistic regression, you normally write GLM. But what is the difference here? Okay, you're going to do the same thing, but only that you're going to say family equal to Poisson. Look at that. I remember when you were dealing with the binary logistic, you're basically going to say family equal to binomial. But right now, you're just going to write family equal Poisson. Because the response variable is basically follow Poisson distribution, which we've already demonstrated. Now, this is the result. Look at the result that we have now. What is this result telling me? I want to tell you this. Because Poisson distribution, Poisson regression model, logistic regression model, they are members of generalized linear model, because GLM means generalized linear model. Because it's a member of a generalized linear model, then the estimate that you have, they're going to be called the log odd estimate. Even in Poisson regression, we call this estimate the log odd estimate. Don't forget, when we're dealing with the logistic regression model, we normally refer to those estimates as the log odd estimate. We are also doing the same in the Poisson regression model. The estimate that we have right now here, they are the log odd estimate. But when you take a look, they are the log estimate. Okay, so now when you take a look at what I have here, the p-value now, the p-value is less than 0.05. It's basically significant. The predators are significant. How do I write the model? Look at the way to write the fitted model. You're basically going to write the log lambda high equal to that. So take a look at that. Log lambda high equal to that. Now, what is the next thing we want to do now? How do we now interpret? Okay, how do we interpret? Now, this is the situation. When you were talking about in the logistic regression, we call the estimate log odd estimate, right? Now, we also have a version of the log odd here, but we don't call it that. We're going to say for Poisson regression, for Poisson regression, Okay, if you take a look at what I have here, we got a log expected count. Log expected count, because we're talking about count, but there's going to be a log expected count for Poisson regression. Now, for instance, I want to interpret my beta naught. How do I interpret a beta naught here? I'm basically going to say that is a baseline log expected count. We also call it a log rate. We don't call it log odd. We call it a log rate or log expected count. Okay. Now that intercept, that beta not equal to 2.94 is a baseline, is the log expected count when all covariate equal to 0. You know, y-intercept is the values of the y when s equal to 0. You know that, right? And that is what we mean. Take a look at that. We interpret beta not equal to 2.94 as the baseline log expected count. Let me repeat this again. The estimate that you see here, okay, in the logistic regression, we call them log odd. But in a Poisson regression, we don't call them log odd. We call them log expected count or log set count. Okay, that's what we call them. I just wanted to take note of that. Okay, now how do we interpret the beta naught of 2.94? That is interpretation. Now, if I say log expected count, if I say log expected count, okay, log, if I have log expected count, if I remove log, what am I going to have? Expected count. And how can I have expected count? I'm going to do exponentiation. Removing log, I'm going to do the exponentiation. And that is what you're seeing here. Take a look at that. If I do the exponentiation of beta naught, then that will give me the expected count. It means I'm actually moving from the log expected count to the expected count. You remember in logistic regression model, when you have the log odd estimate, and I want to move into odd ratio, what am I going to do? I'm going to do the exponentiation, right? That's the same thing I'm doing here. Okay, if I want to go from the log expected count to the expected count, I'm basically going to do the exponentiation, which is exactly what I've done. What am I trying to say now? The exponential raised to power beta naught that gives us 18.9 is the expected count of customers in the baseline group. That is the expected number of customers in baseline group, but that doesn't make sense. It doesn't, you know why it doesn't make sense? When distance equal to 0, when all the predator equal to 0, even when the age equal to 0, then they're still going to have 18.9 customers. That doesn't make sense. We only, at times, I told you the other time, it is not all the time that intercept makes sense. But I wanted to say, why do we need to do that? It may be helpful to center our covariate. But this is not a big deal if we don't care about baseline, because our primary inference is about the increase with respect to covariate. Most of the time, we are not interested in the intercept. We are only interested in whether the predator is significant or not. That is our interest. Okay. Now, let's go to the beta one now. The beta one, we're going to get the beta one. We're going to get the exponentiation of that. Don't forget. Now, take a look at the beta one that we got. Okay, that one is, we interpret that one as if there is an increase. Okay, so as the increase in the log expected count or the log rate ratio comparing districts whose number of housing unit differ by 1. For every unit increase in housing, if housing increase by 1 unit, what do you expect? There will be an increase of that, but on a log scale. That's why we call that. Look at that. If I want to know the number, if I'm not interested in the log, I will do the exponentiation. Look at that. Exponential raised to power beta 1 That will give me 1.00. Now, how can I interpret 1.000, whatever it means? You know, we are comparing districts whose mean housing unit differ by 1. But don't forget, after controlling or adjusting for other covariates. Now, you know, that may not be a big impact when a house increased by 1 in a neighborhood. You can also look at the effect when the house go up by 100. Look at that. Look at the 100 here. What if the house actually go up by 100? What happened? This is just by 1. But by 100, that will give you 1.062. And 1.062 is the rate ratio comparing districts whose mean housing unit differ by 100. Okay, and how do you interpret that? How do you interpret 1.062? If you want to interpret 1.062, you can multiply that by 100. When you multiply by 100, subtract 100 from that. That will give you 6.2%. What are you trying to say? Keeping other factors, okay, constants, but that is adjusting for other covariates, a 100 units increase in housing, okay, unit will yield an expected 6.2% increase in customer accounts. That's what we're trying to say. Okay, 6.2% increase in customer accounts. That is if, you know, 100, if there's a 100 unit increase. You can also look at the effect of 1,000 unit increase. If you want to look at the effect of 1,000 unit increase, plug in 1,000, multiply by what you get for beta 1, take the exponentiation. You're going to see the increase. Okay, now that's for the housing. Now, if you take a look at what I'm trying to show here, it's just to measure the significance of beta 1, okay, using beta 1 divided by that, which is we've already seen that here in the output. Look at the housing. Housing is significant, right? The p-value is very, very small. In fact, not only housing that is significant, all predators are significant here at 0.05. Okay, they are all significant. Take a look at that. Now, I want to talk about the beta 2 now, which is income. Looking at the effect of income, we know from the table the income is significant to the number of customers arriving the store in the region. But if you now want to interpret this, don't forget the slope for income is negative. If you take a look at if you go back to the output, now can you see the income is the estimate is in negative? Look at that, it's negative. Okay, how can that be interpreted? Okay, how can we interpret that? Now, if you want to interpret that, we interpret beta 2 equal to that to be the increase in the log expected count or the log rate ratio comparing districts whose mean income differ by $1. I don't want to say what unit here, but I'm going to say by $1. Okay, and that is what you have. Don't forget, that's a log expected count. If I want to know the expected count and I want to remove the log, what am I going to do? I'm going to do the exponentiation. Take a look at that. The exponentiation of that gives me the 0.99. Okay, now it's 0.99 now is actually the relative rate comparing region whose mean income differ by $1 after adjusting for the covariate. Do you know that $1 is very, very small? You can try $100 increase. You can try $1,000 increase. Let us see now. That's what I'm trying to do here. Here we want to consider $10,000 increase in the mean income. That's what I want to do now. Look at that. 10,000. Now you multiply 10,000 by the estimate. You take the exponentiation. That gives you 0.889. How can you interpret the 0.889? That is a relative rate comparing regions whose mean income differ by $10,000, adjusted for other covariates. And that what we're trying to say is that keeping other factor constant the relative rate comparing region whose average income divided by 10,000 is 0.889. Look at that. When you look at the 0.889, if you subtract, 0.89 is if you subtract from, maybe if you multiply that by 100 in percentage and you subtract it from 100, that will give you 11%. And that will be 11% decrease. Why is it decrease? Don't forget, the estimate for bidder for income is negative. Negative. And look at that. And it's giving you 0.889. So which means that's 11% decrease in the rate for customer visiting the store. Now, we can also do the confidence interval, right? Take a look at that. I can do the confidence interval for the log expected count. I can also do the confidence interval for the expected count. Now, if I want to do the confidence interval for the bidder 1 or bidder 2 or bidder whatever, it's just going to be the estimate plus or minus 1.96. Why am I using 1.96? Because I'm talking about 95% confidence interval, then multiply by the standard error when you go back to the output, right? When you go back to the output, you're basically going to see when you have estimate, you have the corresponding standard error. Look at that. Every estimate. So if I want to find the confidence interval of any of that, of course, I need the estimate, I need the standard error. I'm just going to plug them into the equation. Look at that. That's what I'm doing here. Now, when you take a look at what I have here, the beta 2, okay, the beta 2, that is the confidence interval, the lower end point and the upper end point. Okay, that is for the log, okay, expected count. If I want to do that of the expected count, what am I going to do? I'm going to exponentiate. Okay, what am I exponentiating? I'm exponentiating this guy here, and that is going to give me that. Look at that. That's what I'm exponentiating. Okay, and I can do the same. We're talking about income here, right? For a unit increase, like a $1 difference, right, between the district, right? If I want to talk about the $10,000 difference in, then I'm going to have this. So look at that. Okay, you can see that now. So you can actually construct a confidence interval for the estimate. Don't forget, in the Poisson regression, the estimate is called the log expected count. But in the logistic regression, it is called log odd estimate. But in Poisson regression, it's called log expected count. And if I take the exponentiation of the log expected count, I'm basically going to have expected count. But in the case of logistic regression model, if I take the exponentiation of the log odd, I'm basically going to have odd. Okay. Now, if you want to interpret this guy here, the interpretation is actually here, the 95% confidence interval for the relative rate of customer visiting the store is between that and that for a 10,000 increase in average income for the region. Let me tell you, we don't like working with the point estimate alone because the point estimate could be wrong or right. And that is one of the reasons why to be at the safer side, we normally construct a confidence interval. Okay, and let me tell you, the confidence interval can also do the job of hypothesis testing. I told you the other time, right? Okay, now I want to ask a question now. Based on this model, if we're going to choose a location to build a new store, should we choose area with higher or lower income? Does it matter? You can answer the question based on what you see. If you look at the income, you'll see the income is significant. Look at the direction of that. It's negative. If you look at what we got for that, it's negative. Look at that, income here is negative. Now the question that we are now asking now is, when we are considering to open, to choose, we are going to choose a location to build a new store, should we choose area with higher or lower income? And does it really matter at all? So that's a question that we normally want to answer before going into model. Okay. I think I've presented to you what we call Poisson regression model, just like what I used to say. where we are building a relationship between variable, we care about the nature of the response. The nature of the response variable will actually determine the type of regression that we're actually going to face. If I want to recap this again, when the response variable is continuous, we fit linear regression. But even when you fit linear regression, don't forget you're also going to revisit assumptions of linearity, normality, constant variance, absence of outlier. And for the case of multiple linear regression, don't forget you also need to test whether there's multicollinearity as well. And of course, when the response variable is not continuous but categorical, when it is categorical, you need to ask yourself, do we have two levels? If you have two levels, you fit binary logistic regression. If you have more than two levels, you need to ask yourself, are the levels ordered or not? If they are not ordered, you choose multinomial logistic regression. If they are ordered, you choose an ordinal logistic regression. And if the response variable is categorical and the predictor variable is also categorical, you can do the analysis of categorical variable where you are using a chi-square test. And you can also do logistic regression with that. But the one I'm walking you through now is what of in a situation where the response variable is not continuous, is not categorical, but is a count. If it is a count, then you're basically going to use Poisson regression model. You remember what I walked you through on Wednesday that I call beta regression model. When the response variable is not a count, it's not continuous, it's not categorical, but a rate or proportion or something in the region of 0 and 1. It is greater than 0, but less than 1. Then you're basically going to use beta regression model. And I want to tell you in this course, we've gone through a lot of different type of regression model. And you know what? Because you basically want to take a decision in this world, we need to use an appropriate statistical model. If we don't use an appropriate statistical model, I want to say we cannot rely on your results or on your recommendation. If the government or stakeholder or whatever use your recommendation from a very poor model, recommendation from a poor model, I want to say is like a doctor in an hospital using inappropriate medicine. It is not only doctors that kill, okay? It is not only quack doctors that kills. What about those who make policies and these policies actually affect lives negatively? And that is the reason why we need to be careful when we are doing statistical analysis, when we are choosing model, we got to make sure that assumption hold. And that is the reason why you are here. That is the reason why you have to learn statistics, because you need to be able to figure out what appropriate statistical model can be used in a given situation. I remember what Judge Boss said. He said all models are wrong, but he said some are useful. How can we make our model useful? I think I revised that. I said all models are wrong, but we can make them safe and useful. How can we make models safe and useful? We can make models safe and useful if we care about assumptions. Assumption is as good as a model. And there is no any statistical model anywhere in the world without assumption. And before you can go ahead to make a recommendation from your model, you got to make sure the assumption holds. We got a way to revisit that. We have a way to investigate that. You don't just tell me your result. What I care to see is assumption violated or not before we can actually trust whatever you tell me from the model that you are using. And that's what we do. We shouldn't rush. We need to take our time to make sure we use an appropriate statistical methodology. Is there anyone who need clarification before I go today? I want to say officially, this is going to be the last topic. There's no any topic that's going to come up again, but I want to tell you what we did this week. It's not going to be part of the final because it is not in the textbook. This is just additional information because you need to be informed because the world is changing. The world is dynamic. And you need to know the world is like a moving train. And you need to be informed of what is going on. And that's why I have to walk you through the beta regression, the multinomial regression, and the Poisson regression that we did today. I can assure you will never form part of the final exam, but just for information. Is there anyone who need clarification before I go today? The final assignment will be released on Monday. I decided not to release any assignment this week. Like you're only going to have 9 assignments in the entire semester. So the last assignment will be released, and that is just going to be the end of the assignment that we're going to have. Make sure you stay safe and have a very beautiful day and a very lovely weekend. Bye for now, everyone.